All right, this is section 4.5, integration techniques, specifically substitution. This is the last section in chapter 4 that we're going to cover. Our objectives are to evaluate integrals using substitution and to solve applied problems involving integration by substitution. And the vocabulary is integration by substitution. You kind of get the idea that that is the main idea of this whole topic. So the general concept here is that every rule that we had with differentiation has a way to undo it. So we had, for example, the power rule. Well, we've already learned how to undo the power rule. That's the one where you take the exponent, you add 1, and then divide by the new exponent. That's undoing the power rule for derivatives. Well, the next one we're going to learn is a way to undo the chain rule. There are ways to undo the quotient rule and to undo the product rule as well. This is not something that we will get to right now. So we're going to learn how to undo the chain rule first. So if we kind of recall that the chain rule said that you take the derivative of the outside portion of the function and then you multiply that by the derivative of the inside function. So for example, if we took the derivative of this natural log right here, we would do 1 over the entire argument, which is this piece right here. Then you multiply it by the derivative of that argument, which is the inside piece right here. Then basically you would just put this on top, multiplying it by the 1, and you would end up with that final answer. So it follows that if I wanted to integrate this thing right here, which is what we've got right there, if I wanted to integrate that, we should somehow be able to get back to this. And notice that there's a plus c on there because we could technically add any constant to the end of that, and it would still be considered the same function, just one of the family. So if you're wondering about the absolute values for the natural log, technically, yes, I think you probably still should write the absolute values there, especially if you don't already know. In this case, it was okay because the whole thing had a positive domain, but I would strongly suggest, again, just leave the absolute value bars there. It's just safer. So we're going to be able to integrate this somehow by recognizing that it was the result of a chain rule of another function. The main idea behind this is what's called integration by substitution, probably more commonly called u substitution because we typically use the variable u as our substitution. It doesn't have to be, but that's pretty common. Most people will call this u sub. So the strategy for integration by substitution. What we're going to do is we're going to determine what the inside function is, and here it is. We're going to call it u. Usually that's the variable. Doesn't have to be, but that's usually what we use. And when I say the inside function, what I'm talking about is the function that is the most composited function. So if you had a function that was within another function and then another function inside of that, the most composited piece is typically what you're looking for. But we typically look for the inside function. What could an inside function be? Could be the denominator of a fraction. Technically, that's an inside function. It could be the exponent of an exponential. It could be what you're taking the log of, a whole bunch of different things. Then you're going to find, well, you'll let u be that inside function. Then you're going to find du dx. Basically, you're going to solve, you're going to take the derivative of that u function with respect to x, and then you'll solve it for dx. And again, we'll go through all these steps as we do examples. Then you're going to replace u and dx in the integral and then simplify the integral. The goal in that step is to obtain a simplified integral completely in terms of only u. If your integral does not simplify nicely, you might need to try and find a different u value or just a completely different method. Then you integrate, and then you substitute to put the integrand expression back into terms of x. That's what you started with. All right. So let's go ahead and walk through an example. So we're going to go ahead and look at the example above. We already know what the answer should be because it's at the very top of the page. If you look at this, now the composited piece here would be the denominator. So you would let u equal that denominator, as you see we've done here. Then you're going to take the derivative of that, du dx. Well, if I take the derivative, we end up with 4x cubed minus 9x squared plus 2. That's du dx. Then we want to solve this for dx. So you have to do a little bit of algebra. We'll multiply the dx to the right side like you see in step 2, And then to solve for dx, you're going to divide everything by what's in parentheses. So then you get dx equals du over 4x cubed minus 9x squared plus 2. Now what I'm going to do is I'm going to replace in the original integral, I'm going to replace all of this where the dx is. It's going to go there. And then u was all of this. So as you can see, we put the u there and we put the dx right here. And the nice thing about this one in particular is what you can see is that that cancels that. So then you just end up with 1 over u du. That's going to be a really simple integral for us to do, which we'll show on the next page. So then the integral or the antiderivative of 1 over u is the natural log. Again, I suggest that we put the absolute value bars there, natural log absolute value of u plus c. Then we'll just go ahead and replace the original u value, which was this thing right here. Again, I suggest leaving the absolute values unless you absolutely know that that is positive. And then don't forget your plus c because it's an indefinite integral. Okay, let's go ahead and take a look at a couple of examples, and hopefully you'll be able to follow this. So what I've got in example 1 is I've got the integral of 3x squared times the quantity of x cubed plus 1 to the 10th power. Well, 3x squared is not really composited. There's nothing inside there, but it's pretty clear that x cubed plus 1 is inside of a parentheses, which is being raised to the 10th power. So that's going to be my u value. I'm going to start off by saying that u is x cubed plus 1. And then I'm going to need to find du dx. Well, that's just the derivative of the right side of this thing, which is 3x squared. What you should notice, by the way, is that 3x squared matches the 3x squared that I have on the outside of the parentheses. With any luck, that's going to make everything go away that we need to. So then we're going to multiply both sides by dx. And then we're going to solve for dx by dividing both sides by 3x squared. So we get du over 3x squared equals dx. Okay, so now we're going to take the information that we just found. We're going to replace that in the original function. Okay, I didn't do anything with my 3x squared here, but I am going to replace the x cubed plus 1. That's u. And then I have to replace, trying to make a 10 there, it's not working. Then I have to, still not working. Then I have to replace, that's better, the dx with du over 3x squared. So times du over 3x squared. And the nice thing is here, now I can simplify. That 3x squared there is going to cancel that 3x squared in the denominator. And what that leaves me with is an integral of u to the 10th power du. Everything is in terms of u. Now we simply take the antiderivatives to integrate this thing. So the antiderivative will be 1 over 11 u to the 11th plus c. But again, we didn't start off in terms of u. We need to go ahead and put this thing back into its original x's. So it's going to be 1 over 11. Replace u with what it originally was, which was x cubed plus 1. X cubed plus 1 to the 11th power plus c. And that's it. So the biggest thing is recognizing that you have a composite function of some kind, an inside piece, that when you take the derivative, it's going to get rid of the variables on the outside portion. That's what we're looking to do. Okay, example 2. Looks like definitely have a denominator there, and within that denominator I have something in parentheses being raised to the 5th. That definitely looks to be the most composited piece. So I'm going to let u equal 1 plus x squared. And I will tell you, by the way, this takes practice. Okay, this is not something that most people just can jump on and see. Enough practice and you'll start to be able to see when you need to do it, but it definitely takes practice. So don't get frustrated if you happen to pick the wrong thing first and you have to start over again. So now we'll take du over dx, which is going to be 2x. We'll multiply both sides by dx, which is 2x dx, and then we'll solve for dx by dividing both sides by 2x. So du over 2x equals dx. Okay, now I have everything that I need to go ahead and replace the stuff in my integral. So I'm going to have the integral of 2x divided by, u was 1 plus x squared, so now that'll be u to the 5th, and then times my dx, which is du over 2x. And again, as you can see, the 2x's will cancel out. So now I am left with the integral of 1 over u to the 5th du. And I'm going to rewrite that because 1 over u to the 5th is going to be easier to take an antiderivative of if it is u to the negative 5 du. So now we can bring this up here. The antiderivative of u to the negative 5, let's see, we add 1 to the exponent, so it's u to the negative 4. And then we divide by negative 4, which is the same thing as multiplying by negative 1/4, and then plus c. And then I'm going to go ahead and replace the u value with 1 plus x squared from the beginning. So negative 1/4, 1 plus x squared to the negative 4th power plus c. All right, one more example here on this. Example 3. Actually, it's 2 more examples, excuse me. Yeah, I want to make sure it wasn't a 5th one down there. All right, example 3. In this case, letting the denominator be u doesn't do me any good, because if I let u equal x, then du is just going to equal 1 dx. That doesn't do me any good for that natural log on the top. Okay, I have to figure out a way to simplify that natural log. So the most composited piece that we're going to use here is the argument of the natural log, which is 3x. So we're going to let u equal 3x. Actually, that's not right, because that's just going to give us a derivative of 3. See, even I have to sometimes stop and think about it. So what we want to do actually is let the u value be the natural log of 3x. I think that's going to work for us. So again, don't get too frustrated if you pick the wrong thing and you start moving down these pages and you're like, oh, that's not going to work. It's not going to get rid of everything that I needed to do. Just know that sometimes this happens. I just caught it before I went too far. So let's do du over dx. And that's going to be 1 over 3x times the derivative of the inside, which is 3. Simplifying that, the 3's are going to cancel out there. And that's going to give me 1 over x. I need to solve this for dx, so we'll multiply both sides by dx. So du is 1 over x dx, and then I need to solve for dx, so we'll multiply both sides by x. So x du is dx. So now we should have everything we need to go ahead and integrate. So the top is going to become u. The denominator stays x. dx now becomes x du. This one's really nice. X's are going to cancel out. And all I have to do is integrate u du. Add 1 to the exponent is u squared. Dividing by 1 is the same as multiplying by a half. So we get 1/2 u squared plus c. Replacing the u value with the natural log is going to be the natural log of 3x squared plus c. And there you go. Okay, example 4. We're going to take the integral of x e to the x squared dx. The most composited piece, actually the only composited piece here, is the x squared. It's the exponent of e. So we're going to let our u value be x squared, where du over dx is going to be 2x, multiplying both sides by dx, and then dividing both sides by 2x. Solves for dx for us. So now we can go ahead and integrate. So we'll get x, whoops, meant to change the color there. So we'll get the integral of x e to the u times dx, which is du over 2x. And this is the first time we've seen this happen. The x and the 2x don't exactly match, but that's okay. The constant out in front doesn't matter as much, but these x's here had to go away. Now that 2 in the denominator, really it's just like having a 1/2, because 2 in the denominator is the same as 1/2. And one of the rules of integration is that you can pull a constant out to the front. And that's quite okay if that happens, because the constant can be put in later. So now we just have to take the antiderivative of e to the u, which is e to the u. So we get 1/2 e to the u plus c. And then don't forget to replace u with its original x value, which was 1/2 e to the x squared plus c. And that's it. That's our 4 examples. Okay, let's go on to the next page. All right, so we can use the method of substitution to evaluate a definite integral. The only thing that's changed now is the fact that we have bounds. We treat this exactly the same, except now at the very end, we actually have to plug in numbers. This is one is you have to be really, really careful. In this case, it says round to the nearest thousandth, so this must be something that we actually have to use a calculator for at the end. We'll get the exact answer, and then we'll see what it comes out to as a decimal. But the biggest thing you have to be careful for is you have to change this back into x. If you plug your numbers in before you change it back, you're going to have a problem. There's actually a second way to do it, and if we have time at the end, I might walk through that. Let's see, I've got this example, and then one more example at the bottom of the page. We'll see if we have time. Okay, so let's go ahead and figure out, well, the most composited piece of this one definitely looks like what's under the square root. So we'll let u equal x squared plus 3 du over dx is going to equal 2x. Okay, so du is going to equal 2x dx, and then du over 2x is going to equal dx. We've kind of done that similar thing several times. Okay, so now let's go ahead and put this back into our integral. Now, technically, you should not write your numbers on here because you are no longer going to be in terms of x's anymore, and the 0 and 1 are bounds of x, not in terms of u. So I tend not to write these until I go back to the end. So we're going to write 5x square root of u, and then our new dx is du over 2x. Once again, the important thing here is the x's are going to go away. I can take the 5 over the 2 out to the front as a constant, 5/2. Integral, I'm going to rewrite the square root of u as u to the 1/2 power, just to make it a little bit easier to take an antiderivative. Now I'm ready to take the antiderivative. So u to the 1/2 is going to become u to the 3/2 when I add 1. Dividing by 3/2 is multiplying by 2/3. I'm not going to put a plus c here because I'm eventually going to have to go ahead and evaluate at my bounds. So now I'm just going to simplify. So that's going to be, let's see, the 2's are going to cancel out. It's going to be 5/3. And I'm going to replace the u now, because this is the important part, as x squared plus 3 to the 3/2 power. And now that I've put the x's back in, now I can evaluate that at 0 and 1. So let's go ahead and see what we come up with. So we're going to get 5/3. If I plug 1 in there, 1 squared is 1 plus 3 is 4, so I'm going to get 5/3 times 4 to the 3/2 power minus 5/3. If I plug a 0 in there, I get 0 plus 3, so that's 3 to the 3/2 power. Okay, we can simplify this a little bit. So 4 to the 3/2 power actually works out to be a nice number, because really that's saying I'm going to take the square root of 4, which is 2, and then I'm going to cube it, so that's 8. So I'm going to get 8 times 5/3, which is 40/3. The next one here really just doesn't simplify very nicely, and this is where that whole decimal is going to come into play, because 3 to the 3/2 does not simplify to a nice whole number. So now we'll just plug this into our calculator and get a decimal approximation, I believe we said to the thousandth spot. And I am getting 4.673. 4.673. And that's our approximation for that integral. If they ask for an exact answer, this is the exact answer. If they ask for the decimal, the 4.673 is an approximation. Okay, one more. This one will be the most challenging one of all of them. All right, and it says assume that x is greater than -2. That's going to probably because we're going to end up with a natural log in this thing, so we needed to assume that. But in this case, if I let u be x plus 2, might look like it's not going to work. It is the only composited piece here for us to use, so that's what we're going to start with. So we're going to have u equals x plus 2. Again, this one's going to be a little tricky, and I'll show you what happens here in a second. So du over dx is going to equal 1, which means that if I multiply the dx to the right, 1 times dx is just dx, so du simply equals dx. So if I was to go back and substitute, and this is where the trick comes in, I'm going to get x over u times, in this case, replacing the dx is just du. Well, the problem is I didn't get rid of the x. Everything is not in terms of u. Well, here's the trick. We can actually create that. What we have right here is an expression that involves x's and u's. If I was to take that expression and I were to solve that expression for x, I'm going to bring this down here, that means that x would actually equal u minus 2 if I subtract 2 on both sides. So x is going to equal u minus 2. Well, then I can actually replace the x in my integral with u minus 2 over u du. And you might look at that one and say, well, wait a minute, that really hasn't done me any good, because now I'm still left with a fraction. I am, but don't forget, you can separate fractions over a single denominator. So we're going to rewrite this as u over u minus 2 over u du. And then we're going to simplify. So really what that gives me is 1, because that's u divided by u, minus 2 times 1 over u du. And the reason that I did that is because now I can take antiderivatives with respect to u. The antiderivative of 1 is just u. Antiderivative of 2 times 1 over u is 2 times a natural log of the absolute value of u. And then plus c, because this is an indefinite integral, there were no bounds. So now all we have to do is go ahead and plug back in the original u value, which I've already forgotten what it was x plus 2. So we're going to go ahead and plug that back in, and what we get is x plus 2 minus 2 times the natural log, absolute value x plus 2, and this is why the x value had to be greater than or equal to -2. If I left the absolute values off, it wouldn't work, but we'll leave the absolute values on there. And that's it. So that was the trick. If you end up with something that looks like this, and you're like, oh, it doesn't get rid of anything, check to see if you can manipulate the original equation to simplify what's left over, and then see if it'll work. That's probably the most tricky ones that you'll get. All right, that should be enough. I'm not going to cover that other way of doing it. I think this is probably the best way. It's really the only way that you'll need to know for this. If you are curious about it, I can certainly create a supplemental video. Somebody just let me know, and I would be happy to do that.